Hello, this is Brian Auten. Today's interview is with Robin Collins. Robin is professor of philosophy at Messiah College. His training is in physics and in philosophy, and he is a leading advocate for using the fine-tuning of the universe as a design argument for theism. This is often considered one of the more contemporary and persuasive arguments from design. The purpose of the interview today is to learn more about the fine-tuning of the universe, explore what this means in a case for design, and answer common objections to the fine-tuning argument. Thanks for joining me for the interview today, Robin.
Oh, you're welcome. I'm glad to be here.
Well, first off, would you mind just giving our listeners a bit of background about yourself and the work that you're involved in?
Okay, my main area, well, a little bit of background about myself. I graduated with 3 majors from Washington State University back in the 80s. Major in philosophy, physics, and mathematics, and completed all 3. And then I went to graduate school in theoretical physics at University of Texas at Austin, and really felt a sense of calling to do philosophy. So I applied to University of Notre Dame and went there. And at that time, after 2 years of graduate study in physics at University of Texas, and then I went to University of Notre Dame, and I was focusing on philosophy of religion, but eventually I got back into this issue of fine-tuning, and which I've been working on, probably started about 12 years ago, and have been published a lot of articles on it, and have finishing up 2 books on it, one dealing with the physical cosmology aspects and one dealing with more the philosophy and theology. And I've got several grants for it. And then I've done a bunch of other works on mostly in areas of science and religion, philosophy of physics, philosophical theology, philosophy of religion. Mm-hmm. So I've got quite a few, about 40 publications.
Great. Well, I'm excited to talk to you today about fine-tuning. So I know many of our listeners will be familiar with this to some extent, but let's just start at sort of ground level. What is fine-tuning, and what are the kinds of fine-tuning that we observe in the world?
Well, usually the fine-tuning refers to the fact that the universe is extremely precisely structured for the existence of life, and this has been something discussed since the 70s. And so it's the basic structure of the universe is set just right for life in a very, very precise ways. Now, I think it's not just life that is the relevant factor, and I can explain that later, but it's actually for embodied conscious agents who can make moral decisions. So it's beings like us, not necessarily that look like us, but can make choices that are morally relevant. So if you want to give an analogy for what the universe is like, it's like a biosphere. You know, they construct these. They actually constructed one out in Arizona, but a biosphere is something you could place on another planet, and everything would be set just right within inside, so human beings could exist, the right atmosphere, intake of energy, and things like that. And so things would have to be extremely precisely set for that biosphere to work. The universe is like that. In extraordinary ways, it has to be precise. And now most of the fine-tuning that's been discussed is for life, which I think the relevant one I said is embodied conscious agents, but there's a whole new area of territory I've broken into, and that's only been hinted at and mildly discussed, and that's for, it also seems to be set just right for the existence of scientific technology and our ability to discover the universe. In fact, I think optimally so.
Well, it's fascinating. Now, I wonder, just from the perspective of contemporary physics, is this fine-tuning at all in dispute, or is this sort of the accepted observation by people?
I assume you're asking about mainstream physicists who have actually looked into the subject. Okay, and in that regard, there are several cases of fine-tuning that are not in dispute, and one of those has to cosmological constant or dark energy density, the value of what's called the vacuum energy for the Higgs field is a fundamental field of physics. It seems to be set just right, and the quark masses, which are the constituents of protons and neutrons. And then another one is primordial density fluctuations. Those are fluctuations in density that gave rise to galaxies. Even a skeptic like Steven Weinberg accepts these. Now, there's other cases that are in dispute. So, and part of my first volume of my book is to shore up these cases. And also I've broken new ground into other cases. I also mentioned another area that's not in dispute, and that's one of the initial conditions of the universe, that the universe started off in an extremely low entropy state, which means a very, very unlikely state from perspective of statistical mechanics. So highly ordered state, and that's another case of fine-tuning. So I'd say certain cases are not really disputed. There's other cases that are. But even the ones that are disputed are enough to make the case.
Well, you do sort of have three strands that you mention in your writings: the laws, the fundamental constants, and then the initial conditions. Can you sort of describe the differences between those things? When you're talking about a law, what should people think of? Or a constant, maybe they hear that word, but they don't really have a grasp on what that may be. Can you describe the differences between those, and then maybe give some examples of how you mean that they are fine-tuned?
Okay, so what a law of nature is basically, it's a kind of rule of nature, and it says how it's supposed to operate. And it's usually written in a form of a mathematical equation. So there's, for example, the law of gravity, and that says masses attract each other. And it tells the masses to attract each other by, it's called in proportional to the amount of mass. So if you weigh twice as much, you have twice as much mass, your body, the Earth will attract you twice as much. And it also gives a relation between the amount of attraction and the distance. If you were twice as far away from a mass, then the attraction will be 1/4. If you're 4 times as far away, it'll be 1/8. Okay, that's what you could call a law of nature. Gravity is a good example, and there's other laws of nature that say, for example, that like charges repel each other and unlike charges attract each other. And to say that the laws are fine-tuned means you have to have just the right set of laws, like set of rules, in other words, for the universe to support life in my sense of embodied conscious agents. Now, a constant of physics, if you think about, let's focus in on the law of gravity. If you just you have just a law of gravity which says masses attract each other, that's not going to be good enough. You're also going to have to say the amount they should attract each other. And so you could say, well, attract each other proportional to the mass. But then you need a number that specifies the amount. That's called a constant of physics. So a constant of physics is just a number you have to put in the equation. So I don't know how your listeners are familiar with the law of gravity, but I can give Newton's basic law of gravity. It's force equals mass, g, that's the gravitational constant, times the value of the first mass times the value of the second mass divided by their distance squared. And that g tells it is necessary to tell it how much, that number, which is called the gravitational constant.
Now, what about the initial conditions? Can you talk about that?
Well, according to current cosmology, the widely accepted theory of cosmic origins, the universe started in a Big Bang, which means in our visible universe, if we look around at the galaxies and things like that, about 13.7 billion years ago, those were all that matter was squished into less than the size of a basketball. And that matter had to get galaxies and to get life and have stars, it had to have a very precise arrangement. You can think of it an analogy to get a human body. If you looked at a zygote, and you just take it out and you looked at it in detail under a microscope, very powerful microscope, you would see it was intricately structured. It wouldn't look that way on the surface, but it just looked like a blob of protoplasm. But under the microscope, it would have to have an intricate structure of the DNA and the rest of the sort of organelles in the cells to form a human being. So similarly, the universe has to be in an extremely precise state and that's the initial conditions, is arrangement of mass energy to get galaxies, stars, and ultimately to get life like ourselves. That preciseness of that is measured by what physics call phase space, which is a space of possibilities, and there's a standard probability measure that can be put over that say how probable it is to be in this part of that space of possibilities. And so when you do those calculations, as, for example, Roger Penrose at Oxford, leading mathematical physicist at Oxford University has done, it turns out to be enormously fine-tuned, 1 part in 10 to the 10 to the 123rd power, unimaginably small number. And when we can talk about it later, how, an analogy to how small that number is, but if I'll just say what it is, 10 to a power means, like 10 to the 3rd power means 1 followed by 3 zeros, so that's 1,000. 10 to the 2nd power is 1 followed by 2 zeros. So this is 10 to the power of 10, which that number 10 raised to the power of 123. So if you can imagine it, it's 10, and then put a power of 10, the superscript of 10, and then put another superscript of 123 on top of that 10. And so the number of zeros is just, it'd be more, the number of zeros you would have after the 1, and if you had like a 0 the size you would have on a regular sheet of paper, those zeros would extend clear across the universe. So, it's 1 part in that. That's how precise we're talking about.
That's just an example of, say, one.
That's one, the entropy. Yeah,
but
that's an initial condition.
Mm-hmm.
It's not quite a constant, it's an initial condition, but it is a number that tells you how precise the arrangement of mass energy had to be.
So let's say you have these, the laws are fine-tuned, they all have possible ranges that they could fall into, but only a very narrow range per law or constant would permit life, you're saying. And so you've got this astronomically large, small probability of life permitting ranges in each constant, and then roll them all together and take them all together, and they've all got to be right in that range for there to be the life. Is that sort of the idea in a nutshell, would you say?
Yeah, that's the idea in a nutshell. Let me just go through each one of them. You have to have the right laws, which are the principles of physics. So you have to, like things like gravity. You would have to have the laws of electrostatics that tell charges to attract or repel each other. You have a bunch of other laws, of examples of those, about 14 if you want to count those. So those are the basic kind of principles you got to have in place. Then for each of those laws, or for that go into those laws, there's a set of basic parameters which physicists have called constants. They're just numbers, and they have to be enormously fine-tuned. So that's set just right over a large range of possibilities. That's the fine-tuning of the constants or the fundamental parameters of physics. Then the third is the initial conditions of the universe, and that's just what I mentioned with the case of the very low entropy, very precise arrangement of the mass energy that the universe started off with. So you have 3 distinct types of cases. The first 2, there's many instances that fall under the first 2. The last one, they're just about the range, only one instance, and that's the initial conditions. There's only one initial condition, and that's the arrangement of mass energy at the beginning of the universe.
Can you give any other examples of how finely tuned that the numbers are? Some sort of visualization.
Okay, I'll give you two other numbers. You'd ask for two constants here, the strength of gravity and the cosmological constant. Let's look at the strength of gravity. That's the number G that we talked about. And in that strength of gravity, there's a huge range gravity could be in. And one way of thinking about the range is in terms of the strong nuclear force is the strongest force there is. That's the one that holds the protons and neutrons together in the nucleus, because protons repel each other. So if you had like helium, the protons would be repelling each other. So you have to have another force. That's an example of another law that you need in order to have nuclei at all. That's the strong nuclear force. And that force is extremely strong compared to the gravitational attraction of the protons. It's 10 to the 40th power stronger. That's 1 followed by 40 zeros stronger. So that's the kind of scale for the strength of gravity. So gravity could be 0, or it could be all the way up to the strength of the strong nuclear force. If you think in terms of a ruler, it's like a ruler stretched all the way across the visible universe, which is the length of that ruler would be about 15 billion light years. And a light year is the distance light travels in a year. Light travels 186,000 miles in a second. And there's 86,000 seconds in a day, and there's approximately 86,000, and there's 365 days in a year. So multiply all those together, that's how far light travels in a year. Then multiply that by 15 billion, that's how far we're talking about. So imagine this ruler stretching across the universe. That's our scale. The strong nuclear force would be at the very end of that ruler. That's its strength. The current strength of gravity would be in the first trillionth of an inch. Okay? If gravity were not within the first, let's say, millionth of an inch, if it were anywhere else, beings like ourselves would not be possible. In fact, it's even less than millionth of an inch. There's this really small region at the beginning there it has to be in, compared to that entire ruler. So that's one way of visualizing it. So if you thought of an old-fashioned radio receiver, and I use for my students WK Life, you've got to tune in WK Life. So you're flipping G, which is the gravitational constant. You just randomly flip it. It would be in WK Life comes in that first little teeny region at the beginning of the ruler. You'd have to land in that teeny, teeny region in order for any kind of beings like ourselves to exist in the universe. And so if you look at, kind of a straightforward calculation of probability, it seems to be about 1 part in 10 to the 38th, which is 1 followed by 38 zeros, which is approximately 1 part in a billion, 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 billion. So it's very, very finely set it has to be. If you look at the case of, that's one of the cases. The other case is the cosmological constant, or dark energy density. Dark energy density in the universe acts as a repulsive force, pushing matter apart if it's positive. And the energy density can actually be negative, even though it's very counterintuitive. If it's negative, it will act as a strong attractive force. So let's just look at the case of it being positive. If it's very much positive, galaxies, the matter is coming out of the Big Bang, when the universe is exploding, would move apart so quickly, galaxies and stars could never form. So it has to be very, very small, the dark energy density. And when physicists have made these calculations, it comes out to be, compared to its possible range, 1 part in 10 to the 120th power, which is 1 part in 1 followed by 120 zeros. If it were larger than that, galaxies couldn't have formed. That's, by the way, the most discussed case in the cosmology literature, the fine-tuning. And that's the one had led Steven Weinberg to propose this multiverse explanation, which we'll get to later. So there's a couple more examples. The cosmological constant is probably considered the most impressive case of a constant being fine-tuned.
But again, even if they were taken on their own, they're astronomically, amazingly fine-tuned, but you have to roll them all together as well. So
right.
How does that affect the probabilities, say, exponentially?
Well, if they're independent, you multiply the probabilities together. So you would multiply 10 to the 120th power times 10 to the 40th power times 10. If you get multiplied by the entropy, then you get an extremely small number. But the entropy is small. You hardly can get any smaller than that. So in some sense, you can multiply them together. That's one way of doing it. Another way of doing it is thinking of them as just independent lines of evidence that the universe is fine-tuned. So another way is thinking in a courtroom analogy. In a court, let's suppose you have a defendant up there on trial. So you have one piece of evidence, fingerprints on the gun, okay, that indicates guilt. But it may not be enough. But let's suppose you have witnesses saw the person, going into the building where the person was killed. Okay, that would be another independent line of evidence. And let's suppose then you had DNA evidence both on the gun and around the body. That would be another independent line of evidence. When you took those all together, you would have an extremely strong case for guilt. So even if a person questioned one of them, let's say, well, how did you quite measure the fingerprints? Maybe they weren't his fingerprints, or maybe there's some other explanation. It would still, the whole case would still stand. That's what philosophers call a cumulative case argument, because you have independent lines of evidence indicating the same thing. So you think they all couldn't be wrong, and if any one of them was right, it would be enough to establish guilt. So likewise here, if any one of these things were, completely held up, it would be enough to establish fine-tuning, and there's lots and lots and lots of them. So that's another way of thinking about it. You get an extremely strong case for fine-tuning that way.
Well, I think that is really helpful because when we look at theistic arguments, we tend to take them as a cumulative case together in that way as well. So we have to look at the fine-tuning you're saying in the same way, is that it's sort of cumulative case for fine-tuning all these different constants and laws then.
Yeah, and I want to give you another analogy with the cosmological constant, the strength of gravity, how small these numbers are. So, and then one for the entropy. So if you threw a dart, let's say, and you were going to try to hit a single proton, which is very small. I mean, it's not just the size of an atom, but much smaller than the size of an atom, and you were coming from outer space, it would be much more probable for you to hit that single proton you picked out than for the cosmological constant to be that value. It'd be peanuts in comparison. And in the case of entropy, you could think of it, another analogy to think of it is, let's suppose, a building, it all crumbles, and you take dynamite, and you're just going to place the dynamite in the right place, right ways, so that the building will all come back together, like, in a reverse photography, where you go one direction, you watch the building collapse, and then you turn it back. And if all the masses were just going just right, in reversing their trajectories, the whole building would come back together. So it would be physically possible to place dynamite in just exactly the right ways, where the whole building would come back together, and all the furniture in the building would come back together. But it'd be enormously improbable. It's far more improbable, the initial conditions of the universe. Nothing compared to that.
So what is the theistic argument that you formulate for the fine-tuning of the universe? How do you formulate that or present that in a brief form?
Okay, there's two different ways I formulate it. One is very intuitive, but the other way is more rigorous and is helpful when you answer objections. So I consider two separate hypotheses for explanations or responses to the fine-tuning, or three different ones. Is the theistic response. Okay, God did it. The other is what could be called the brute fact hypothesis, or single universe brute fact. It just is one universe, and it just happens to be the case that everything is just right in the universe for life to occur. So we're just extraordinarily lucky. It just happened that way. Okay? And the third one is the multiverse, which is there's many, many universes. And I'll get to that later, but I want to focus on the brute fact one now and theism, and offer a reason to prefer the theistic over the brute fact. So the brute fact says it just happened by chance that we have life. So this is analogous to, let's say you have a roommate in an apartment, and he's a biology major, you're at college, and you open it up and you go back to the back, and there's mold growing, and it grows into just the face of Abraham Lincoln. It looks just like Abraham Lincoln. You wouldn't say that happened by chance. You would say, hey, your biology major was doing a, clever artistic design, because it would be so improbable for everything to be arranged just in the face of Abraham Lincoln. So you have two factors there, the reason you don't accept that it was just by chance. One is it's very improbable. The other is there's something special about it, namely, and the face, it looks like the face of Abraham Lincoln, and special in the sense you can glimpse alternative explanation, a way of making it not improbable, namely your roommate. Similarly, or another analogy would be an ink spill. Any ink spill is very, very improbable, but if it comes out to a face, there's something special about that. We wouldn't just accept it by chance. I'll give one final analogy. Is that if you toss the coin 100 times in a row, any sequence is extremely improbable. But what if it all came up heads 100 times in a row? You wouldn't just think that happened by chance. That would be the last thing you would accept. You'd be looking for an explanation. There's something special about heads every single time. So similarly, when you look at the universe, it just seems enormously improbable or enormously surprising that it's this way. And there's something special about it, namely it gives rise to beings like ourselves. And we can glimpse an alternative, an explanation that takes away this surprise, namely a theistic hypothesis. So just an analogy to what we do in these other cases, the last thing we should accept is the brute fact hypothesis. So that's one way I go with it. There's a little more formal way to take this into account, and that says, works off of what you could be called the surprise principle. That's just a layman's way of saying a certain kind of principle standardly accepted in what's called confirmation theory. So let me give what the surprise principle is. Okay. It says if you have some a body of evidence, some occurrence. You have an occurrence, and if it's more surprising under one hypothesis than another, then that occurrence counts as evidence in favor of the hypothesis that's least surprising under. So the more surprising it is under a hypothesis, the more it counts against that hypothesis. So let's consider the case of fingerprints on a gun. Why do we take fingerprints on a gun typically to be a sign of guilt? Well, and the fingerprints matching the defendant's fingerprints. Well, we take it as very improbable they would match. It's possible somebody else had almost identical fingerprints, but we take that as very unlikely they would match if the defendant was innocent, but not surprising if the defendant is guilty. Hence, we conclude that evidence supports guilt over innocence. It's not doesn't actually prove it beyond a shadow of a doubt, beyond any doubt, but it counts as strong evidence. So similarly, this case of the structure of the universe, you have the same sort of thing going on, very, very unlikely under a brute fact that the universe is just here, but not unlikely under theism. Hence, it's very strong evidence in favor of theism over that hypothesis.
Well, very good. Now, I know that there are some objections out there to fine-tuning argument. So I want to kind of throw various common objections and maybe some different questions that come up that at least I've heard. I think maybe someone like Professor Richard Dawkins might say something like, well, we all thought biology was designed because, it appeared designed, but, along came Darwin and showed us that we don't need a designer. Now, physics is just waiting for its own Darwin to come along and show us we don't need a designer to explain the appearance of design. So, Robin, how would you respond to that sort of objection, or perhaps if you want to call it a hand wave?
Okay, the analog to the Darwinian explanation in the case of the fine-tuning is the multiverse hypothesis, which I notice you have a question later on. Let me say why it's an analog. So that alternative explanation, the Darwinian analog, is already out there being promoted. Okay, the Darwinian explanation of organisms consists of chance variation in the offspring, like chance genetic variation or chance variation in the structure of an organism, plus natural selection, which means those organisms that are the most fit survive and the other ones die off. So that's how the evolutionary explanation works. In the case of the multiverse, it's the same thing as the idea, and this is the leading alternative explanation to theism. I mean, if you were asked cosmologists about this, almost all, and did not want to accept theism, almost all would go to a multiverse. So the multiverse is the idea there are not just one universe, but there are many, many, many universes, and each universe, its structure is different. So if you have enough universes, eventually one will have just the right structure so that beings like us can arise. And then so that's the chance variation. And then it's no surprise, they say, that we observe our universe to be fine-tuned because we wouldn't have existed otherwise. So that's the observer selection. So among all the universes that have observers, the observers are only going to be able to observe fine-tuned ones. Also no surprise that we, as randomly selected observers, observe our universe to be fine-tuned, and that's what they call the observer selection effect. So it's really just a parallel to the Darwinian explanation.
And so about the thing there where, this is just the appearance of design, it's not really designed. The explanation is, look, there's just countless universes out there, and we just happen to be the lucky one that can see this.
Right, and there's countless, so eventually one of them arises, and every time one of them arises, the observers can only observe universes that are fine-tuned, and so it's no surprise we observe a fine-tuned universe.
Mm-hmm. All right, another question then. Now, if we're arguing that the laws and constants are fine-tuned for the possibility of life, basically, a few possible questions or objections on this one. And first, what is meant by life? Couldn't there be other kinds of life out there that we're not familiar with?
Okay, there's two parts to this question. One is whether there's other kinds of life in our universe that we're not familiar with. And that's fine for the fine-tuning argument. Let the universe be populated with life. It would still have to be fine-tuned in order for that life to exist. So maybe there's Klingon, Romulans, Borg, all that's out there, right? And that still doesn't affect the fine-tuning argument, because in order for those beings to exist, the universe would still have to have just the right structure, okay?
Yeah.
So the objection you're really trying to get at is, couldn't there be universes that are different in structure that have life forms that, let's say, are not based on carbon or are different kinds of life forms? So what the fine-tuner is saying, well, you have to have just the right conditions in order for there to be life. The objector is saying, well, that's assuming life only can occur, has to have a certain kind of structure. I claim, no, that's not the case. All that's, first of all, embodied conscious, first point is embodied conscious agents are the relevant kind of life because, remember I said it has to be unsurprising under theism, and what makes it relevant, that body of data, because that's the way, it's very surprising to occur under one hypothesis but not under another. Well, the only way you can see it's unsurprising under theism is there has to be some good reason why God would create a particular kind of life, and so it has to have value. And I don't think there's much reason we can see bacteria or crystals or viruses would themselves have value, but we can see that in the case of agents like ourselves that can make choices. There seems to be a kind of value that arises, like courage, self-sacrificial love, those sorts of things. So we can glimpse a reason why God would have created this sort of universe with those kinds of beings. So that's really the relevant kind of life. Now, that kind of life requires everything we know about it. Embodied conscious agents requires a lot of stable, reproducible complexity. You can do simple thought experiments to show that you cannot get that stable complexity unless things were just right. For example, let's look at one of the cases of the right sort of law. Let's suppose there was no strong nuclear force. If there were no strong nuclear force, that's what held the protons and neutrons together, the only kind of atom you have would be hydrogen, because if you tried to get helium, for example, you have two protons, the protons would repel each other, and the nucleus would fall apart. So you would have hydrogen gas throughout the universe. A universe composed of hydrogen gas is not going to have embodied conscious agents. You just can't get stable, reproducible complexity with hydrogen gas. Another example would be in the case of the cosmological constant. If you don't get galaxies and stars forming, you don't have energy sources for life. You don't have any place for them to exist at. And so you just have matter. It blows apart so fast, the matter just becomes thinly distributed throughout the universe. No room for stable, reproducible complexity because you can't get the conditions for it. So it's a very minimal condition we're asking for, stable, reproducible complexity that can go through an evolutionary process. And you just don't get that in a lot of these cases by very straightforward arguments.
Okay, well, you opened up a lot of stuff there that I want to keep looking at. You've defined, like, minimally what life would be and talked about, Star Trek characters. You didn't say Star Wars characters. That's a point against you.
Okay.
But, no, I'm kidding. But and we talked about, there could be some other sort of life. But the thing that I want you to elaborate on more is I hear the objection along the lines of why fine-tune for life? It could be fine-tuned for rocks or hydrogen. But you mentioned there and started to sort of answer this question, but I want you to elaborate. You mentioned it being part of a confirmation that, this would be something God would want to create. I mean, because some people would say, come on, look at all the hydrogen out there, or, hey, the universe is more fine-tuned for death because, there's more death than there is life. So they kind of look at it as sort of whatever you find the most of, then that's what it's tuned for. But go back to why embodied conscious moral agents and elaborate on that some more.
Okay, well, we have to look at an analogy because we're looking at what counts as relevant evidence. There's all kinds of features of the universe that simply aren't relevant. So let's go back to our courtroom analogy. Typically, if they're just kind of scratch marks on a gun, they count as, no one brings them up as relevant evidence. Why? Because there's no reason to think a particular, pattern, every gun will have some scratch marks on it. You look at the scratch marks. There's no reason to think that pattern of scratch marks is less surprising under the hypothesis the defendant is guilty than if the defendant is innocent. But we have a reason to think that in the case of fingerprints. If the defendant is guilty, then it's not surprising the fingerprints match. They fall into this pattern. But very surprising under the innocent hypothesis. So you have to look at in that case, what's making it relevant is there's a difference, a differential in surprise under one hypothesis versus another, the two you're looking at. Now, let's do a further thought experiment. Let's suppose we knew there was these fingerprints on a gun or a knife, and we knew that a certain kind of serial killer always leaves, has kind of a certain kind of paranoia or neurosis that he leaves a certain kind of scratch marks on his gun. If we found now scratch marks on that gun, a certain pattern, now they suddenly would become relevant, because given that neurosis of that defendant, it's no longer equally surprising under the innocence and guilt hypothesis. So now that becomes a relevant piece of evidence. So going back to the case of the fine-tuning, what we have to look at is what about the universe makes this differential in surprise? There being, rocks or, so many moons around Jupiter is no more less surprising under theism than under a brute fact hypothesis. Just like if I throw up, 100 coins and they come up all heads in a row, that's no less surprising under theism than brute fact. They're both very improbable. But in the case of life, you can glimpse a reason in the kind of embodied conscious agents that I'm talking about. We can glimpse a value that those agents have. Now, the theistic hypothesis is not just God's a designer, but God's a perfectly good designer. And so what we would expect such a being to create is a universe that exemplified value, because that would be the only thing that would motivate God to create something. Won't need any kind of expectations about God, what God would will, because otherwise we have no guidance on what God would will. But if we know God is good, we know God's going to create a universe that has a better balance of good over evil, let's say. So we can glimpse a value in our existence. We can't glimpse a value in just there being hydrogen and nothing more. Why hydrogen and nothing more versus, any other kind of universe? So those cases, there's no differential in surprise. In the case of embodied conscious agents like ourselves, there is a differential. So it suddenly becomes relevant evidence. And what you do in these cases, just like you do in the court cases, you take all the relevant evidence together. So you if there's a piece of relevant evidence, you include it. So in the case of the court case, if the scratch marks are relevant because the defendant, the serial has a certain kind of neurosis that makes them likely to put these scratch marks on a gun, then they suddenly become relevant. So you add them to the fingerprint evidence. And so here what you do is everything that might be relevant, everything you can glimpse a reason why God would do it, you include as part of your evidence pile. And so you would include embodied agents, not just hydrogen. The goodness is the key. I mean, the goodness of God is key. If you didn't have goodness, a generic intelligent designer, there's no confirmation given to that. So it has the goodness, because the goodness gives you an expectation about what God would do.
Mm-hmm. All right. Well, here's another objection. How about this? Some might say that there are just some fundamental laws out there that are maybe yet to be discovered that will explain why the constants are this way. So if some other laws were discovered, would that undermine fine-tuning at all?
Well, let's look at the extreme case where we have a final theory. Physicists are searching for a final theory, some master set of equations that explain everything else. And let's suppose that final theory entails the values of all the constants. So given that final theory, we can completely explain why those constants are what are. In fact, that was the hope of superstring theory, but kind of got busted about 10 or so years ago, that it would do that. Even if that were true, then it just pushes the issue of surprise up one level. Why that final theory versus any of the other ones that would entail different values for the constants? So why it'd be very surprising that the actual set of final laws would be such that they would entail just life-permitting values under chance than non-life-permitting values. Now, under theism, it wouldn't be surprising that God would, that'd be a very elegant way to do it, create a final set of laws that just gave you all the constants. So it's not surprising those laws would exist under a theistic hypothesis, but it is under the non-theistic hypothesis. Here's another analogy which you could use for that. Let's suppose you had a final theory that not only implied the constants of physics, but also implied all the initial conditions of the universe and determined everything else. Okay? So we have a complete explanation from that final theory why everything occurs. That still would not take away. It would still be very improbable. Let's say I found, I go up to the mountains and I find rocks arranged, welcome to the mountains, Robin Collins, just in that pattern. It would still be very improbable. And I have two hypotheses. My brother was up there and arranged them, and they just happened, earthquake happened, they follow in that pattern. Even though that final theory would explain it, it would still be very improbable that that would happen by chance. And versus my brother hypothesis, I would still say it was strong evidence my brother was up there and arranged them. Why? Because I would say of all the final theories there could be, it would be extremely improbable that it would just be the one that would entail this to happen. But it's not improbable if my brother did it. So there's still the improbability still occur. And you don't have to decide that question of whether there's such a final theory that would entail all the initial conditions and constants to make those ordinary inferences. So similarly in the case of the fine-tuning.
We've talked a bit here about the multiverse hypothesis and maybe some ways that this could account for the fine-tuning or explain away the fine-tuning. So are there variations on the multiverse view? Do these variations, take different approaches to how they explain fine-tuning? And, what would you say is the main weakness of using that as a explanation?
Well, there's two variations of the multiverse hypothesis, two major categories. There's one, what I call the universe generator version. There's some underlying physical process that generates these universes. And that's what inflationary cosmology, and the multiverse generated by the concept of inflation, where there's a free space in which is rapidly expanding and generates bubble universes whose constants are slightly different. And so it gives you a variation in constants, and then there's this observer selection that occurs I talked about before. So eventually you get a universe with just the right values for the constants under that scenario. The superstring, that Stephen Hawking is promoting in the grand design, that does that same kind of hypothesis, except it's using superstring theory, that underlying dynamic to generate mini universes. So that's one kind. It's a physical process of doing it, giving you those universes. The other kind is metaphysical, and that's just the idea that all possible realities exist. So every possible set of laws that could exist, and every possible set of constants is instantiated somewhere. So there's some world when a being just like me is president of the United States. There's another world, anything you can. There's the Star Wars world, if it's logically possible. There's the Star Trek world. There's the Lord of the Rings world. Every world you see in every single science fiction or fantasy, if it's possible, it exists under that hypothesis. So that's the two major ones. And let me start with the universe generator version. For obvious reasons, the all possibilities one is not nearly as popular. It seems like most people find it kind of outrageous to think that's true. But so the universe generator version is by far the most popular. Now, there's a couple of objections to the universe generator version. One is if you look at the details of it, and I've done that for the case of inflationary cosmology. That's been published. Other physicists and astrophysicists have looked it over. It requires to generate the universes, there has to be just the right laws and mechanisms to do it. So to a large extent, it just pushes the question of design or fine-tuning back one level to the universe generator itself. Why those laws versus all the others? So we have fine-tuning again at another level. The other response is, as a matter of fact, it doesn't really explain the fine-tuning of the constants. And the reason is that it's still very surprising as it uses the observer selection effect. So that's real critical to it. So they would say as a randomly selected observer, it's not improbable that I see a fine-tuned universe. Now, let me say why that's extremely critical. Under a multiverse hypothesis, every kind of improbable occurrence will occur somewhere. Okay, so I gave you the example of the coins coming up 100 times in a row on heads, fair coin. That will happen somewhere. A being just like me will observe it happen because there will be a universe in which that happens. You get a wide enough variation in the multiverse. Well, you don't want the multiverse explaining that away. So if I observe that to happen, you don't want the multiverse saying, well, no problem, no need for an explanation. It's going to happen somewhere. Because if you do that, every single kind of probabilistic inference gets undercut, and science and all their everyday inference just collapses because it explains everything. There's no need for any other explanation. Everything we consider improbable, not improbable. So they don't want to do that. So to avoid that, what they say is that the coins coming up this way, a randomly selected observer would be very unlikely for, although some observer will observe that, it's very unlikely any randomly selected observer would observe that. So it's very rare for an observer to observe that. So the improbabilities here is me as a randomly selected observer will observe the coins come 100 times in a row. So I can still claim it's very improbable. Good so far?
Yeah.
Okay. So then now comes the problem, and it's really nicely illustrated in the case of low entropy. What makes the low entropy so intractable is that this multiverse objection or hypothesis was raised to the low entropy of the universe once the idea of entropy and probability was first developed in physics, called statistical mechanics, around 1900. By Ludwig Boltzmann. He raised this idea that maybe there's many, many universes. That explains it. The immediate objection was that it's vastly more probable for an observer to rise as a fluctuation in its local region is ordered, but the rest of the universe is disordered, than for the whole universe to be ordered as we observe. And so it doesn't explain why we're not what they call Boltzmann brains. A Boltzmann brain is just an observer that fluctuates into existence, has the order of a brain structure, so it can observe things, but then only lasts a very small amount of time and is surrounded by chaos and disappears. That's how most observers will be under this normal measure in statistical mechanics. To understand that idea, let's give a couple of analogies. One analogy is back to my 100 coins. Let's suppose the 5 coins in that 100, let's suppose I have 100 laid out, on a sequence, like a table. They're just in a line, and they're restricted to that line. And let's suppose 5 coming up in a row on heads is enough order for there to be observer. That's the analogy. Let's suppose I shake it. It's way more probable to get sequences of 5 in a row, and then, the other ones being random, heads and tails, then for all of them to come up heads. So what we would expect is, under random shaking, we would expect isolated kinds of order, just enough to get an observer. Another analogy would be monkeys typing on a typewriter. Eventually, Shakespeare will be produced if you have enough of them. But it's vastly more probable for them to get a paragraph that makes sense, and the rest is chaos. So if you looked at, you had every universe, you had a monkey typing on a typewriter. In one of those, Shakespeare will be. But in most of those universes, the vast majority, you will have mostly junk with isolated paragraphs that make sense. That's isolated order. So that will be the vast majority of ordered arrangements, the paragraphs that are ordered. Let's say that's the equivalent of an observer. The vast arrangement of paragraphs that make sense, that are sufficiently ordered to make sense, will occur in text that are just chaos everywhere else. Only very, very rarely will it occur in a whole complete set of Shakespeare. So similarly, under the multiverse hypothesis, it's even if there is a multiverse and it's just random, it's extremely, extremely unlikely that we would find ourselves as observers in a universe that's ordered throughout, that we're not just isolated, not simply ordered throughout, but that there's other beings around us. We're in a part of a community of beings. That's enormously improbable, and that's what we find. So it doesn't explain it. Well, theism does, because if we're going to have possibilities of moral action in the world, courage, and there has to be other beings around. Can't just be isolated. So what you get is just you just re-get the probabilities in the case of entropy. You get you just push the improbability now to why we're not isolated observers, what they call Boltzmann brain or fluctuation observers. Now, what I've shown elsewhere, it's on my website, is that this actually, the same objection comes up with other constants. So it's not just the low entropy case. Now, it's widely recognized in the low entropy case. Like you could say, look at Closer to Truth and Roger Penrose. That's why he rejects anthropic explanations in terms of multiverse. He doesn't see it helping at all because of this problem. So that's widely accepted, called the Boltzmann brain problem. But what I show is really hits the other instance too, and so the multiverse really doesn't give, the universe generator version doesn't give a good explanation of that problem.
Well, thank you, because I finally understand what's meant by the Boltzmann brains, because I've heard it lots of times, or read through it, and just didn't fully grasp it, but that really makes it clear.
So you can see it in the case of the monkeys, right? If you had the text, you'd have most meaningful paragraphs would be surrounded by chaos.
Yeah. Mm-hmm.
Yeah, because it'd be so unlikely for the whole thing to not to be ordered to all make sense. So that second problem, the all possible realities version, it really infects that one to an enormous extent, because order, our world is very ordered in terms of its laws, and has a simple, intelligible order. If you think of possible patterns, a universe could be in arrangements of mass energy, and that's what the laws are. They describe the arrangement of mass energy, and that arrangement of mass energy in the universe happens to be simple, follow in simple patterns that we can put down in equations. But of all the possible arrangements, most do not fall into any kind of simple pattern at all. Very complex patterns that we'd not even be able to grasp. So they're what we would call very disordered. So the vast majority of realities, possible realities, are going to be very disordered. And just like the book of Shakespeare, it would be vastly more likely to have local regions of order and the rest chaos among possible universes than the ones that have order throughout. So once again, you get this overwhelming expectation that we would be Boltzmann brains if the possible universes was true. But it's not just now in the case of entropy, it's the laws themselves. It's everything. So as one Peter Forrest had put it, a philosopher, what he called rubbish universes, rubbishy universes, the ones that are just, they're like the ultimate messy room, are vastly more likely than ordered universes. And by the way, for people listening, it's you can see that. That's why if you have trouble keeping your room in order, that's the reason. is because disordered arrangements are vastly more likely. So unless you put energy in to keeping everything ordered in the room, because there's so many more ways of being disordered than there is of being ordered, it's vastly more likely your room goes to a mess if you don't do something about it. And that's why buildings crumble. That's why bridges fall. All those processes are dependent on that idea. So that's a really crucial idea in physics and understanding the world. There's vastly more ways of disorder than order.
Mm-hmm. And it gets exponentially worse the more kids you have. Is that?
Yeah. So especially worse, right? So that really presents a huge problem for the all possible realities exist and even the universe generator version. So you've got a problem arising that doesn't really explain. It doesn't explain everything we know. That not only we exist as observers, but we're observers in an ordered universe that we can understand, that we can interact with. We're not isolated from each other. That's why I call embodied conscious agents, because we're agents within the community. And then there's a whole additional stuff that the universe seems to be fine-tuned for technology and discoverability, just kind of adds to that. So it doesn't really explain that.
Well, just briefly, I know some people might hear about fine-tuning and they might Google it and find, say, the book by physicist Victor Stenger, and he's got one called The Fallacy of Fine-Tuning, Why the Universe is Not Designed for Us. So, I mean, what briefly would his view be? What reasons would he have for calling it this is a fallacy? And do they carry any weight, do you think, against the case that you're making here?
Well, I'm rolling my eyes when you mentioned Victor Stenger. His arguments are pathetically bad. He misunderstands physics. This is one of those books that could be, thrown in the junk heap. But it's what he wants to say is he has various criticisms of the fine-tuning argument. He mostly doesn't know what he's talking about. Now, I have a response to him. We did an Oxford Dialogue Series on Christian Theism, which is coming out soon, and I have an expanded version of that on my website. Mm-hmm. And physicist Luke Barnes has done a detailed response to him published on the Astrophysics website, and now it's going to come out in the condensed version of it in the Australian Journal of Astrophysics. There are just so many misunderstandings he has. It really is pathetically bad. And I could just go through some of the stuff he says, like he thinks that he criticizes me, for example, when I mention there needs to be gravity. Well, he says gravity would exist in any universe because, he says, it comes from the idea of point of view invariance, which he takes to be that the physical laws have to remain the same no matter what point of view you look at them from. So that's a condition of objectivity. Something is objective means that if it's still the same event, if you look at it from your description of it, ultimately what it is the same no matter who's looking at it. Okay, that makes sense. But then he says, then gravity has to come out of that. This is, and you can just think about that for a minute, and you can see he's completely confused. We can understand what a world would be like without gravity. Without gravity, masses wouldn't attract each other. Well, what would that mean? You could imagine a universe in which all the masses moved apart, and no matter, even if there were some places where there was a more density of mass than others, they would still be moving apart. It wouldn't make a difference about the rate they're moving apart. That would be a universe without gravity. It would be a completely objective universe. Simply cannot get the law of gravity from objectivity, because you can describe completely objective universes that have no gravity. In other words, masses, when they get close to each other, don't tend to come together. They still move apart, okay, when they're closer together. So gravity is actually something we discover. Another one that's appalling is what he says about the low entropy. He thinks you can explain the low entropy by the size of the universe. The universe started off with small size. That was refuted over 30 years ago, Roger Penrose and others, and what they imagine is you have a universe that's expanding, then it stops, and it collapses, which is one of the possible models in general relativity. The entropy is still increasing, and the universe is shrinking in size. So the size, how small size, does not explain the low entropy, because it's going to continue increasing even if the universe now is collapsing. And there's a whole bunch of other objections to that. You could just do simple calculations that show that the entropy is really extraordinarily low from what it could be. Everyone accepts that. This is standard physics and cosmology. And Stenger thinks he has a new explanation. No, it's an old explanation from the 70s that's been shown for many reasons to be completely false. So he, thinks he knows something everybody else doesn't know. Then he explains, like another issue, he's explained the smallness of the proton mass. That's one way of understanding why gravity is small, is thinking the proton and neutron mass are small. And he attributes that to, that's because the protons and neutron mass is coming from the quark masses, which are a result of what's called quantum corrections, which is there's a certain amount of mass that comes with a quantum correction, so it's because those are small. Yeah, that's okay, but the whole problem is why are those so much smaller than what they could be? And if you looked at the physics literature, that's the problem everyone discusses. So he's presenting the problem as the solution. And Barnes points this out again and again. So it's like saying, I can explain the smallness of the proton mass because it's composed of quarks and they're small mass. Yeah, but why are they so small? You haven't explained anything yet. So, this just goes on and on. But, look at my website. I have a shorter version of this than Barnes does, but it's not to be even taken seriously at all.
Now, I've heard that you were authoring, or you mentioned at the beginning there, some books coming out. Can you talk just a bit about what those are going to cover?
Okay, the physics and cosmology one, which is the one I'm planning on finishing first, is my title of it is the fine-tuning of the universe for life, technology, and discoverability. So it expands the cases of fine-tuning, that it's not just fine-tuned for the existence of beings like us, but also for the existence, having technology, and for us being able to discover it. In fact, it's optimally set just right for that. So let me give you a couple cases. And some of these, several physicists I've looked over, they check out. These are some of my new cases. But one of them, the one that, I first really came across, I already knew about the discoverability of the laws. People had noticed that, like the unreasonable effectiveness of mathematics, Eugene Wigner, a famous article, and that the laws were seem to be right so that we can discover them. And I had already written something on that. But this goes beyond to look at the constants and those parameters. So I looked at the case of what's called the fine structure constant, which measures the strength of the electrical and magnetic interaction. Electric force and magnetic force are unified in current physics, so it's really electromagnetic interaction, and a fine structure constant measures the strength of it. In certain units, atomic units, it's the inverse of the speed of light. So you can think of it as changing the speed of light in minutes. So that's probably more intuitive for people. So let's just think of it in those units, changing the speed of light. So if you decrease the speed of light slightly, you can't get a wood fire going. And the reason is, so that's one direction. If you can't get a wood fire, you can't forge metals. If you can't forge metals, you're stuck in the Stone Age. Okay? So why is that? Well, if you think about a fire, and most people would never have asked themselves this question, but you're standing around a campfire, and you feel heat coming off. What accounts for the amount of radiant energy? that comes off. The campfire is at a certain temperature. Well, what actually accounts for it in those units is the speed of light. It's one of the factors that go in. It's these fundamental constants determine it. So if you decrease the speed of light, for that same temperature, the amount of radiant energy is coming off increases. If you were to imagine turning a knob and decreasing the speed of light, you'd get more radiant energy coming off. Now more energy would be leaving the fire through smoke and radiation than being produced by combustion. That forces the temperature of the fire down because energy has to be conserved. If you do it very much, the temperature is forced down to such a point that fire will just go out because it has a combustion temperature, so you won't be able to have wood fires. If you go in the other direction, you get an increase in, so that's one direction, no wood fires. And you can already see it. It's very close to the edge because if you just do this in your own experiment, have a stick in a campfire, expose the surface to air where it's not getting radiant energy, it will tend to go out. I have pictures on my PowerPoint presentation of the campfires, exactly what happens. And so it explains why fires are actually pretty difficult, right on the edge to get going. If you go the other direction, then electric motors, generators, and transformers all have to get proportionally larger. So it seems to be set so you can have the smallest you can get, the most efficient you can get electric generators, motors, and transformers, which is central to a modern technology, and also best resolution for light microscopes, while at the same time still being able to have forged metals. So you're just at an optimal point, and there's a bunch of other things that are optimal just like that. So that's one example of new territory it goes in, and it rigorizes a lot of the cases of a much more rigorous treatment than you get anywhere else of the fine-tuning. So that was the idea behind the book, was initially just to rigorize the cases. And now it's extended this. And what happened personally with me is years and years ago, I was not so sure they would hold up because there was all major mistakes I found in the literature at the time, in the more popular literature. But now I'm really sure of the fine-tuning because there's so many cases, and they do more than I thought there were.
So when should we expect those, do you think?
I'm hoping to finish the first one by midsummer, and I'll probably post the drafts on my website. Now, coming out as a book, that always takes to a publisher, and that said might take a couple of years. I know the slowness of those things, but I should have a lot of it put on my website.
All right. Well,
and the second one I'm hoping next year to finish, so I'm pretty close to both of them, but it's taken a long time already. So.
Well, we've been talking all about the ins and outs here of fine-tuning and questions and objections, but as we start to wrap up, what about those who, see the power and the value in using this as part of an argument for theism or Christianity? What would be, the practical application for someone who's not super well versed in this, but, in other words, if you were talking to a layperson, Robin, and you wanted to put this information into, a pretty simple presentation, what sort of tips would you have? How would you encourage people to lay something out like that?
Well, I just encourage them to point out the universe is enormously precisely set for existence. Okay, point number one, that's the fine-tuning. It makes sense. It's not surprising in theism, but extremely surprising if we're just here as a brute fact. So Lincoln analogy, the Lincoln face, and then to point out some of the problems with the multiverse as an explanation, like, even if there is a multiverse, the generators have just the right laws, and there's this well-known Boltzmann brain problem, so it's doubtful that's really going to be able to do it. And then say, well, if they just still want to say something like, well, the universe is just, just happened by chance, that's it, I would say, well, that's not really intellectually honest because you're not applying a double standard here. Why don't you do that in other cases, which you're clearly not doing? Like when you argue for the big, when they argue against, let's say, young Earth creationism and point out the Big Bang, the evidence for the Big Bang would be very unlikely, if God just created it, would make it all look like it was old. Well, you're applying the same sort of probabilistic reasoning there in a whole bunch of other cases, but you're not willing to do it here. You better be able to point out what the differences are if you want to, keep your intellectual honesty. So I'd say something along those lines.
Mm-hmm. Well, are there any common mistakes people make when they're trying to properly understand or present the argument?
They often focus on the special conditions on Earth, like it has to have the right distance from the sun and things like that, instead of the special conditions of the universe as a whole. And the former can be easily explained by the fact that there are many, many planets in the universe. We know there are 300 billion galaxies around that, about 300 billion stars per galaxy. We know a lot of the stars do have planets now. And the universe is probably way larger than the visible universe. So just by chance, it's likely a planet will have just the right conditions. So they need to focus on fine-tuning the universe as a whole, not planets per se.
Okay, that's good. Now, when you're presenting this information before audiences, what do you think has been maybe the most common objection that you've encountered?
The most common objection I have encountered is the who designed God objection. They will say, well, you appealed to God as a designer, but wouldn't God be just as much in need of explanation as the universe? In fact, that's the most common atheist objection to the design argument itself. And I think it's a red herring because they don't really understand traditional theism. If you have an anthropomorphic designer, one that has like a brain and a body, let's say like the Mormons believe in, then you do really have a problem, because then you've just pushed the problem back to who designed that brain and body. It would also need to be fine-tuned. Okay? But in traditional theism, God has been thought to have no unbounded, the attributes are unbounded, omniscient, it means all-knowing, all-powerful, and so no internal complexity. To have internal complexity requires boundaries. Like we look into a watch, there'd be a boundary between, the old-style watch, between the spring, things making the spring, and the gears and other things. So the material has well-defined boundaries. That's what makes it the part it is. So God is, traditionally, for independent reasons, God is thought to have no internal complexity. So if such a God exists, is logically possible, then it explains the fine-tuning. So the only real question is, does the existence of such a being make sense? Is it, what philosophers call logically possible? If it is, it will explain the fine-tuning without transferring it up a level. Okay? So that question of whether it's logically possible still remains. I mean, fine-tuning doesn't remove that question. But if it is, then it explains the fine-tuning. On the other hand, what the fine-tuning does is hugely raises the cost of atheism, because now it's much more difficult to be an atheist because you have to swallow that this just happened as a, say, brute fact, just this universe, as just an enormous coincidence, one part, in 10 to the 123rd power. It's just, that's so difficult to swallow. So it makes atheism, that alternative, so much worse. And because it does that, it supports theism. So that's how I would answer that.
Mm-hmm. Well, Robin, you've spent like a considerable amount of time dealing with, the subject of fine-tuning. And many people, even atheists, would say, this is one of the most powerful theistic arguments. So I'm curious, just, how powerful an argument for design do you think it is?
I think it's a very powerful design. I would say not design, I think theism. Mm-hmm. It's a very powerful argument. It's really hard. Let's go back to the brute fact hypothesis. Do you really believe that it's just one part in 10 to the 10 to the 123rd power that just happened by chance? Do anybody really believe that? I mean, and look at the other cases. It's just very hard to swallow that. So I think it's a very powerful argument. Now, and I think among more lay people and scientists find it the strongest argument. Now, philosophers are their own breed. And so I think a lot of people would find it the most powerful arguments, to put it that way, and I certainly do.
Mm-hmm. Well, if you wanted to point people to further resources, if they want to delve into the topic deeper, where would you suggest for them to actually begin?
I would go to my website and look at some of the articles on there, and especially ones written for more anthologies or more common audience. And also, I might have a PowerPoint presentation, and then look in the references therein, and for further books and things, other people's discussion of these issues, and also the infidels.org. Leading Atheist website did an online book called The Great Debate, Philosophers Debate the Evidence, and there's a good debate between me and somebody else, Paul Draper, on the case of the fine-tuning there. So there they could get the exchange back and forth.
Well, excellent. Now, Robin, I really appreciate all the time you've given to this subject and your work. It's been a real pleasure speaking with you today.
Oh, good speaking to you.